Hello, today is March 7th, 2023. My name is Austin, and this is a clip from my GIS lecture with Professor Matt Kelly at UW-Tacoma. We discuss census data, which exists as percentages and dollars, and we discuss joining that data to census block group polygons so we can compare different urban and rural communities and regions using these dollars and percents. But in order to do that, we need to standardize the dollars and percents from the census. We need to standardize to obtain z-scores. Z-scores make it so we can take dollars and percents, two metrics that are completely different. If we turn them into z-scores, we can compare them on a common scale and score these census block groups on a common scale. And we'll symbolize it and do that as soon as we generalize our information. So up here is Professor Matt Kelly, and he's going to explain how to do that.
So how do we do this? We are going to talk about indexing, which is statistical. And we're going to talk about hotspots and cluster analysis. And both of those are, what I'll present to you tonight, are spatial operations. So we'll be using our statistical data in spatial analyses. All of this stuff is intended to be used in the pursuit of pattern recognition. We are looking for patterns in the landscape, predictable patterns in the landscape, or at least statistically significant patterns in the landscape that we can use to make decisions. Those decisions may be, say, in Susan's case, where are we going to perform environmental interventions to deal with toxic runoff? They may be, where are we going to put proper signage to warn people that there are bears nearby, in the case of Diana's project. It may relate to how we are reestablishing Oregon white oak in some of our parks. All of these projects take multiple variables into consideration and then make decisions based on how those variables interact with each other. In essence, if we were to draw this out using polygons, if we've got, it's kind of like a Venn diagram, right? You remember Venn diagrams from your logic classes, maybe? If these are all polygons that represent positive indicators of this or that, then we're looking for the areas of greatest overlap. This little space at the center of 1, 2, 3, 4 polygons represents a site where we have 4 overlaps. Here we've got 3. Those are patterns, right? Those are those are spatial patterns that emerge when we begin overlaying multiple sets of data. That's a simple overlay. That's just, let's count up the number of polygons that overlap and talk about magnitude. Indexing our data enables us to not look at things as just unique occurrences, but as dimensions of phenomena in the landscape, environmental or human landscape. So we index factors like population density, median income, could be soil type or elevation, slope. These are all variables. How we index those data is kind of complicated, though. It's not terribly complicated, but it requires a little bit of thinking. So suppose that we are indexing a single. I'm gonna talk about shape files rather than feature classes or geodatabases. So let's say that we have a polygon shapefile, and I'm saying shapefile because it's a little more legible than me talking about a feature class with features in it. So we've got a shapefile that's full of polygons. Because it's the type of data I'm most familiar with, let's call those polygons block groups. Okay, so let's say we're working with census data, and these are block groups. All right. The attribute table of our shapefile consists of an ID. There's our GeoID. Every file has that. And then in our attribute table, we have a series of rows. This is our attribute table. So we have an attribute table that consists of an ID and then a bunch of columns. What are these columns, anyone? What do those columns represent?
Different census data.
Census data, fields, yep. Census data, fields, let's call them variables. Okay, census data, fields, variables, that's what we are dealing with. Forgive me, I did this last week too. I'm refreshing my parking. Okay. So those census data, the shape files themselves, they include variables, and those variables, they can be anything. So Jesse, you're working with census data. Yes, a little bit. So what are some of the fields that you're working with?
Age, education, gender, ethnicity, occupation.
Okay. So age, what format does that data take?
Numeric.
Okay, so what does it look like?
5-year increments. So 0 to 5.
Okay.
And, yeah.
Okay, so is that numeric?
Yes. No. I don't know.
Yeah. What about let's come back to it. 0 to 5 is one of the age ranges, right? 0 to 5, 5 to 10, 10 to 15. Okay, those are ranges of age. You said ethnicity.
Yep.
And and what does that look like? Those numbers or words?
That's gonna be text. So that's gonna be text. Hispanic, non-Hispanic, white, black,
yep.
Asian.
Yep. Okay. Got any numbers in your data set?
Income.
What's income look like?
I guess it'd be average income, so 100,000. I guess it'd be the same as age, so it'd be the variable.
So income's a little different than age. Okay, let's write it down. Age is a nominal variable. Okay, so when you're looking at your data, people, start thinking this way. Age is nominal if it's ranges like 0 to 5, 5 to 10, 11 to 15, whatever it is. Those are nominal ranges. All right, those are essentially named categories. Okay, that's one type of data. Income for the census, that can take a lot of forms. I'm going to go with median income by block group. Okay, so that's one of the variables that the census offers. That is not nominal data. That's simply statistical. Those are integers. That's an actual number. So like $50,050 or 47,234, something like this. Those are whole numbers. Income. All right. So we've got integers. We've got nominal data. We can have scaled data, like survey results. 1, 2, 3, 4, 5, 6. That represents a range of data, but those numbers carry value. We can also, I'm blanking on what I was going to say next. Levels of education. are similar to scaled data. You might have high school graduate, middle school graduate, elementary school graduate. You may have percentages. So we might have, say, percent under the poverty line. Okay, so that would be a percentage, right? Which would be like a 0.51. That's really high, a 0.03, and so on. The thing to be aware of here is that nominal data are not comparable to integer data, are not comparable to percentages. Those are all different forms that data take. Indexing these data requires you to make decisions like now about how you're going to make those data speak the same language. How do you make them similar, comparable? Okay. So, Austin, your hand just went up.
Yes, hello. Can you hear me?
I can.
Awesome. So like you were saying, I have some data that I will be downloading from the census that will come in the form of integers. It'll come as median family income and also income disparity, for example. And that will come, I imagine, as a dollar amount, but I need it to exist as a percentage, so, because all of my scoring using my metric system is on a scale of 0 to 100%. But now my matrix is asking me for things that exist as like median family income and income disparity. How is the best way to go about turning that into percentage? Do I base that on area median? Or what?
This is exactly where we're going. So we need comparability, right? Our data need to take similar forms. Percentages. All right. So I'll just say first off, raw numbers are never good. So like total population is no good. Total number of people that did this or that is no good. Those numbers reflect biased populations, right? The total number of people that did this or that depends on the total number of people that are in the unit we're analyzing. Proportions are always necessary. We have to normalize, and this is one way that Austin is thinking of this. So we have to normalize our data to make them comparable. We can normalize by converting to proportions. All right, so percentages, those are absolutely comparable. The percent of people that graduated high school with a diploma, the percent of people that drive a car, the percent of people that ate at Burger King last week, those are normalized variables. Okay, so we can normalize using proportions. Generally, we normalize by area or we normalize by total population. Okay, those are our options. So you can divide the total number of people that did this or that by the total population of that unit of analysis. Okay, so that's just the simple formula: total variable pop divided by total pop. Okay, there's your percentage that did this thing or that thing. You also can divide your pop by area, right? So your total population that did this or that by your total area of the unit that you're analyzing, whether that's a block group or a block or a neighborhood or a school catchment area or a bioregion like a watershed or a drainage basin. We can normalize by area. All right. Either way, we generally refer to this as something like density, right? So the density of the population that did this or that thing, areal density or population density. Okay, that's normalizing, but that doesn't help us when what your problem, Austin, is that you have median income alongside a bunch of percentages, right?
That's right.
Yeah. So that's how do you make those numbers comparable? Because that's a little more complicated.
Definitely. And then like median monthly mortgage as well. It's like median monthly mortgage compared to, subjective to what? Like I need to do like the average in the state, or is the median kind of canceling that out for me?
No. Okay. So
this is about that.
Yeah, no, and this is good that we're doing this tonight because this is exactly where I was going. You gave me a perfect segue. It's almost like I paid Austin, like I'm a magician and Austin is my plant,
It's literally the most stressful part of my project so far.
Really?
So I'm glad you're enjoying it.
I'm just going to draw it out then. God, Austin, I'm not sure what we should do.
Well, I'll bang
No,
my head on the wall a couple times.
I got you, Austin. I know what we should do. This is what I wanted to talk about tonight. So, Austin has two different types of normalized data. He's got an average of something, and he's also got a proportion of something. But his average is an average of a giant number. So those two don't talk to each other. This is where we bring in the concept of the z-score.
Oh yeah.
Okay. Or you might call it a standard score. Okay. Means the same thing. It's a pretty basic statistic that you can calculate using some pretty basic math to normalize all of your data. Okay. And the only thing you need to generate a z-score, well, first of all, let's talk about what a z-score does. Okay, so in general, your data curve in such a way that most, so if this is our data, okay, that area in that curve is our data. And then these are, let's say these are just low values, and these are high values, okay? All right. In general, we tend to be fairly normal, right? Most phenomena tend to have a mean. Well, they all have a mean, but most data tend to concentrate around the mean or our average, right? The notion average, right? The burn that you're just normie or you're just average is that you truly are just like forgettable and normal because in general, most of the population, most stuff tends to happen here. This is normal. So we have our, if we're looking at our x-axis, our x-axis here is measuring value of something. So maybe that is income, for instance. Okay, let's say it's income, and then our y-axis here is total population. Okay, so how many people populate this curve? Well, most people tend to fit inside of an area called normal, called average. We can measure that area of normal using some basic statistics, and those basic statistics are standard scores. In order to calculate a standard score, a z-score, we just need two numbers in addition to your sample score. We need to know your mean. We need to know the average of your entire population for whatever it is you're measuring, okay? And we also need to know your standard deviation. Right? This is like your golden ticket. Z-score, you can solve so many problems with z-score, with standard score. So if you know your mean and your standard deviation, then you can calculate a z-score. A z-score tells us, we draw some lines, a z-score tells us how unusual or how normal a particular observation is in our set of data. So I just drew some vertical dotted dashed lines. If all of the stuff that exists in this normal area is average, then as we move further from average, which is that line right down the middle, that's our mean, as we move further in either direction from normal, we approach not normal. And eventually we are significantly different than average. We call these standard deviations. So as we're moving away from the mean in a data set, as our observations are further and further away from normal, we move in steps called standard deviations. This is the amount of variance in the data set that we're measuring. So the more our stuff concentrates around average, the smaller our standard deviations. But they still exist. Those patterns still exist. So if we know our mean and our standard deviation of a data set, then we can take any observation and place it on that continuum. We might know that observation X, for instance, is 2.7 standard deviations away from the mean. Okay? That's pretty significantly different than normal, and that's our z-score. So the way we calculate z-score is not terribly mind-blowing. It is simply your observation, so your observed value, minus your average, minus your mean, divided by your standard deviation. Okay, so take a simple example. Let's say the standard deviation of our data set is 1. And our average for the data set is 2, and our observed value is 3. So let's say we have a standard deviation of 1, we have an average of 2, and then we take a value from our data set that is 3. So our observed value, Jesse, is a 3. Okay, so Jesse minus the average equals 1, divided by 1 equals 1. Jesse is 1 standard deviation above average. Not quite significantly above average, but almost Jesse. Now, Susan, for instance, we might, Susan, let's say Susan is a 6. So Susan, we've got a 6 minus 2 gives us a 4. Susan is 4 standard deviations above average. That's incredible. That's so significant that we might question that result. But that's
I'm an outlier.
You are an outlier. That 4 or Jesse's 1, that's our z-score. Okay. Our z-score is going to range generally from like negative, well, it depends on how many outliers you have in your data set, but let's just say -4 on up to +4, though it's going to go, you'll get z-scores like 15, 20 because you have crazy outliers. In practice, when we're looking for significance, anything above about a 1.5 in either direction, a z-score of about 1.5, you can be about 85% sure that your result is significant. Certainty is probabilistic. We assume statistically that if you're that many standard deviations above or below average, then there is likely something different about you that's not due simply to noise in the population. We aren't all perfectly average. We all range. There's all degrees of average, right? So -0.8 or +0.7, you're average. Maybe you've got blonde hair, or maybe you've got black hair. If you're a 3, then maybe you were born with purple hair. That's very unusual. So we're looking at degrees of normal. This being said, to Austin's problem. So Austin, you have some ratios, right? Your proportions, the percent of people that are this or that, right?
Yep.
Okay. And then what's the other thing you have?
I have median home value, median gross rent, median monthly mortgage, median family income, and then income disparity, which is disparity of financial.
Okay, great. So it doesn't matter. So and remind us of your extent, your area of analysis.
Extent are the block groups of Key Peninsula and Gig Harbor, Washington, which is a total of, now that I've recalculated it, 1, 2, 3, 4, 5, 6, 7, 8, 15 total block groups.
Okay, so Austin's data. 15 is a pretty small sample size. We might want to increase that.
Yeah, I had it as blocks, but I realized the data I needed didn't exist at that fine of a level. So
No, it doesn't. We may want to increase that, but regardless, here's Austin's data. Okay, so you've got your data set with your ID, and you literally, I could probably draw 15 rows. Yeah, we shouldn't make inferences based on 15 cases. So Austin, let's talk about increasing the number of block groups, since that's not a.
I'm open to it.
Okay, so ID is one of those, right? That's your GeoID. What block group is this? Don't do anything with that. That's just your primary key that helps us to identify what particular spatial unit we're operating on.
Right.
One of these, though, is median rent, right?
Yep.
Okay, so median rent is going to be something like, 1,700 for that block group, 2,300 for that block group, 1,100 for that block group, whatever it is, right? And then next to that, you have the, I don't know, let's just say percent. What's one of your ratios?
Let's do percent of population below 150% poverty level.
Okay, percent. So I'm just going to say percent poverty.
Or poverty, yeah.
Right? All right, that work. Percent poverty, we have got like a 0.08, a 0.17, a 0.02, and so on, right? Now, you see the problem, and you already vocalized it. 1,700 does not compare to 0.08. If we were to do something silly, like just index 1,700 and 0.08 by like adding them up, then we would end up with 1,700.08.
Super silly.
Right. So the 0.08 is lost. It doesn't carry near the weight that the 1,700 carries. They're not comparable numbers. So that's no good. So I'm going to erase that. Can't do that. We do, however, want to be able to add these up or multiply them or something, but we need to make them similar. So median rent we need to deal with. What you have here is a set of data in this field called median rent. There is an average of median rent. So what is your mean, median rent for your entire set of data? You need to calculate that number. Let's say, just for the heck of it, that it is, I don't know, $1,800. Okay?
My mean of the median rent.
Yep, there's one number. Got to calculate that. And to do this in Arc Pro, you can simply right-click on your attributes and calculate and click the statistics button. And that'll give you all the data that you need right now, because you don't just need mean, you also need your standard deviation. Standard deviation.
And so you said summary statistics shows that?
Yeah, maybe it's called summary statistics.
I think that's what I've used. Yeah.
Just right click, and then from the context menu, it's statistics or summary statistics. I forget what they're calling it these days.
Yeah, just define the mean of the median. Yep.
So standard deviation is one of the other numbers that's generated there.
Oh, yeah.
And your standard deviation may be like, I don't know, 300, something like that. It shouldn't be too high. If it's too high, then there's probably an issue with your data. But so once you've got your mean and your standard deviation, then you can calculate your z-score. So this is all you need to calculate z-score. To calculate z-score, you're going to create a new field. So don't call it index. Call it median rent z. All right? What does median rent z look like? So you're going to go into your field calculator. So right-click on median rent z. Oh, when you create median rent z, this needs to be type double.
Okay.
Double. Okay. You want to make sure that's a double format variable. It's not text. It's not integer. We need decimal places.
This is when I'm adding the field, or is this when I'm using the calculator?
It's when you add the field.
Okay, thanks.
So median rent z, it's going to be a double type variable or float. If you're in other applications, float and double both give you the ability to add data to the right-hand side of a decimal place. Okay, so that's a double type variable. You're going to use your field calculator once that variable exists, and your field calculator formula will be median rent. Okay, so you're just going to click from the menu of variable options. So it's just going to be median rent minus, what did we say, 1800 in parentheses, divided by 300.
Standard deviation. Yeah.
Yep.
Okay.
That's it. That will give you, for your median rent Z field, a bunch of Z scores. And those Z scores, like I said, are going to range from negative something to positive something. Now, that's all well and good. You've got outliers to deal with, so I'll talk about those in just a second. But I recommend that all of you who are indexing data, you go through and standardize your data, normalize your data using Z-score. There's really no reason not to. It does two things for you. First, all of your values are comparable. A 1.7 for median rent is no different than a 1.7 for percent of population that has a high school education, right? They both represent difference from normal on the positive side of that equation. Okay, so that's comparable. The other thing that Z-score does for you is tease out in a pretty quick and efficient way your significant values. So you don't know offhand. I just wrote down 0.08, 0.17, 0.02 for percent poverty in my little fake chart here. I don't know actually if 0.02 is significantly lower than average, because I just don't know. We'd need to look at the entire data set and run some statistics. So Z-score both makes my poverty variable comparable to other variables, meaning that we're using the same scale. It also tells us which of our cases are statistically significantly higher or lower than average. And that's valuable. So you're going to end up with, if you've got, so in this case, I've got only two variables, poverty and median rent. I'm also going to end up with a percent poverty Z-score. If you've got 6 variables and you're trying to analyze these variables, you are going to need 6 Z-scores. Okay. Unfortunately, you may need to do just a bit more work because your Z-scores likely have outliers attached to them. You can work with Z-scores in and of themselves for analyses, and that's fine. And that's what I'm going to show you with cluster analysis. But if you're trying to index these data, then you probably are, well, no, you're not probably, you're going to need to deal with outliers. So I'm going to take 2 paths now. We're going to branch, all right? On the one side, I'm going to explain to you how to deal with outliers so you set yourself up for indexing data. On the other branch, I'll talk to you about how to run a hotspot or a cluster analysis using your Z-scores as raw variables, and that's perfectly fine. You don't need to worry as much about outliers there, okay? So branch 1, if you're indexing your data. The simplest index, the index that I always encourage you all to do is this. I'm going to stop talking about median rent, percent poverty, median rent Z, percent poverty Z, and I'm just going to start talking about variable 1, 2, 3, 4, 5. Okay, it's just easier to say, okay, because the content really doesn't matter. So here's my attribute table, and I apologize for my parallelograms here, but I'm drawing on my screen, so you get parallelograms. All right, we got variable 1, variable 2, variable 3. Now, in theory, you've been good analysts and created variable 1Z, variable 2Z, variable 3Z. Okay, so far so good. Now you want to index your data. You want to know not just what are the values of variable 1, 2, and 3 at a particular location, but where do we see concentrations or particular arrangements of those variables? Where do we see, say, if we were making a sustainability index, where do we see the greatest levels of sustainability? or risk. Where do we see the most risk if variables 1, 2, and 3 are different measures of risk? All right, so how do we bring these together? Simplest way to do this, and I think it's fairly effective, is simply to add. We might go variable 1z plus variable 2z plus variable 3z equals index. All right. Now, if life were so kind as to provide us with like a 1.5 plus a 1 plus a 0.2, then our index score would be like, what, 2.7. 2.7. All right. 2.7, that's great. Maybe, but we need to calculate all of our index values in order to know if that's great or average or whatnot. We can take an average of our index values. So let's say we added up a whole bunch of these things, and we ended up with like a 4.3, a 1.1, a 7.8, and holy smokes, a 17.9. Up to that point, that looks like kind of a normal range of data. Okay, 1.1 to 7.8, I guess, given the values we're working with. We also do know that we've got only 3 variables, variables 1, 2, and 3. And we know that variables 1, 2, and 3 should range from around a -4 to a +4. I'm actually going to drop the negatives right now and just talk about one side of the, it's called a two-tailed. So that's tail 1 is positive, tail 2 is negative. I'm going to talk about just the positive side of z-scores for now, because when we start working with z-scores that are both positive and negative, things get real tricky. And I'm happy to help you all with that, but let's talk conceptually about something, because there's one more step that you need to take after you create your z-scores, and that is we need to deal with our 17.9. It feels too high. How do we know it's too high? Well, we can, if we were to just do the simple math, take our index and calculate the average z-score of all of our z-scores and the standard deviation, and then get a sense for what our outliers are. Probably 17.9 is like 3 standard deviations above average. So what I'm proposing here is that you reclassify your z-scores before you index them. So step 1, we're going to calculate z-score. Step 2, we're going to reclassify or simply classify z-scores. To classify z-scores, there's going to be multiple ways to do this. There are multiple ways to do this. I'm going to recommend that you, again, for your set of, so you're going to create your index. You'll add them up. Okay. So calculate z-score. I skipped a step. I apologize. To index by adding. Okay. So you just add them up. Variable 1, 2, 3, 4. Add them up together. No, I'm skipping a step. No. I hear pens, and I think it's Susan. I know you're writing frantically. We don't want to add them up yet. I skipped a step. Yeah. The issue that we have here are our individual z-scores have outliers. So we need to reclassify our individual z-scores. So it's a couple steps. Calculate your z-score and reclassify z-scores. I was right the first time. We're doing this for individual variables. So each, so 3, if we've got variable 1z, variable 2z, variable 3z, we're going to want variable 1z reclassified, variable 2z reclassified, and so on. The range of those values we are going to simplify. Okay? because we need to eliminate things like this 17.9. To do that, for any one of your variables, you're going to have to calculate your average and standard deviation. Same process over and over again, and then classify using your field calculator into, say, average, 0, 1, 2, depending on the values that you're using, maybe 3. All right, 0 meaning it depends on your values. When you've got a two-tailed z-score, some values are below average, some values are above average. It depends on how you're weighting your index. If this is a risk index, for instance, then maybe your well, let's not talk about risk. Let's talk about habitat. Or Austin, you're talking about, let's go to your project. You're measuring gentrification, right?
Yeah, residential displacement, sort of good areas and bad areas. And
yeah, good areas and bad areas.
Types of people moving in, types moving out.
Talk to us about median rent. So what do low median rent score? What does a low median rent do for you? Is that a good thing or a bad thing? Is that what you're looking for or not what you're looking for?
Let me think. Like, from my point of view, it is what I'm looking for, but
yeah.
if it's low median rent and it's surrounded by a bunch of indicators of deprivation, then it may not be a good area to look for.
Okay, so you've got a couple of steps. Let's not then. You're going to have to run some analysis on your variables. Jesse? You're indexing.
Yes.
Yes. All right. So you've got what is one of your variables? Median income. Yeah.
Yep.
All right. So you're looking for low median income, high median. You're testing the market. You've determined that high median income people are buying this particular product.
Yep.
Okay. So in Jesse's case, all of this side of his table, they're not useful to him. Okay. So they're his 0. So in his case, a z-score below 0. So any negative z-scores, or really, any negative z-scores are actually not contributing factors. They wouldn't be what he's looking for. So those would score 0. So he would just reclassify his variable 1z, select all of the cases in which your z-score is less than 1, and those get a 0. Select all those z-scores that are in that first range. They're slightly higher than normal. Those are your 1. Little bit higher than normal, say between 1 and 2 standard deviations. A z-score of between 1 and 2, that gets your 2. Anything higher than, say, 2.5, that just gets a 3. Because you know that an 8 is significant, but it's probably ridiculously significant. So you don't need that 8. You're just going to call it a 3. So we're reclassifying your z-scores to eliminate those outliers so that when we index your data, we aren't overweighting the income variable, for instance. Does that make sense? Okay. What we want is to know that for each one of your variables, we've got, say, a 0 through 3 classification scheme. So if I have 3 variables, and I know you have more than that, Jesse, but if I've got 3 variables, variable 1, 2, and 3, and I index those together, variable 1 plus variable 2 plus variable 3 equals a range of values from 0 to 9. Right? 9 meaning that's where we have the greatest concentration of high income, high education, and high likelihood to play sports or something like this. 0 meaning low income, low education, and aren't playing sports at all. So we're standardizing our classification scheme to get rid of outliers so that our index values are legible and meaningful, and we're not overweighting any particular variable. That's a tedious process. Okay, so first you're calculating your z-scores, then you're classifying your z-scores. That means if you've got 6 variables, you're creating 12 new fields. 6 z-score fields and 6 classified z-score fields. You can do all this in a single crazy equation if you want. Write your algorithm in the field calculator, calculate your z-score, and then it's a variable, it's Python, and skip a step. But you're writing all the same script. You're just doing it all in one variable. I'd recommend, for getting this done properly and not spinning your wheels trying to figure the code out, you just create. If you've got 6 variables, you create your 12 new fields and have at it. Your index then is simple. Just add those up. When you add up variables to create an index, so 0 through 9 is my index score. One of the nifty things about indices is that they can take into consideration scaled values. All right, so data that are meaningful, that carry weight, like a 0, not so great, 3, very significant. But they also can be used in a binary way. So let's say that Jesse, in the search for the ideal client, knows absolutely that people who watch reruns of Laverne and Shirley will never buy this particular adult beverage. That's a binary. Somehow he has these data, and it's a binary variable. 0 meaning people who watch reruns of Laverne and Shirley. 1 meaning people who do not watch reruns of Laverne and Shirley. Jesse's equation, let's say he only has 3 variables plus the Laverne and Shirley mess. Variable 1 plus variable 2 plus variable 3. Now, we also have this binary condition. If you watch Laverne and Shirley, it doesn't matter how great you are, you're not buying that beverage. So we're just going to simply multiply by variable 4, the Laverne and Shirley variable. Laverne and Shirley, remember, is a binary 0, 1. Now, our range is still 0 to 9, but we know that anybody who watches Laverne and Shirley, no matter how awesome they are otherwise, will not be purchasing the adult beverage and gets a 0. Okay, so for habitat analysis, people, if it's often the case that if you're too far from water or too nearby to roads, too nearby to human settlement, you've got some great binary variables. John, thinking about your project, where the cow is going to roam, there's a lot of binary variables, I think, at play in your work. Cows are not going to be walking across deep bodies of water. They're probably going to be avoiding certain deep bodies of water, Jesse. Not shallow. So use those. You can use those binary variables in your work to complicate and also add nuance to your results. Really, what it does is take out of play features or observations that might otherwise be wrong. So indexing, lots of z-scores, lots of reclassifying. Now, interestingly, this works just as well for raster analysis. And I'll talk about rasters in a minute, but we're basically doing the same thing. For this example, I've been talking about an attribute table with lots of attributes in it. Imagine, however, that variable 1, 2, and 3 were raster data sets. Yes? A raster data set is a grid in which every grid cell contains information. We can know for every grid cell whether that's higher or lower than average. So we can know its z-score. And then we can reclassify those grid cells based on their z-score values. This equation works just as well if variable 1, variable 2, variable 3, and variable 4 were raster data sets. To do that, you wouldn't be performing the operation in field calculator. You could use raster calculator, or raster calculator, or something like weighted overlay. Okay, those are both tools in Spatial Analyst that provide you the ability to overlay raster data sets. and generate index data, right? Informative data that can be used to make decisions. You can certainly create your variables in your vector data sets and then convert them to raster if you do want to overlay that way also. Okay, these are just the stats. Now let me pause. I'm saying a lot, and I know I assume a lot of you when I'm talking, so I'd love to answer questions before I go too far and you lose whatever questions you had. So are there any questions?